Then we are going to continue with the second part of the lecture today, which focuses on the problem, what actually happens if the Gaussian assumption that I have about my constraints doesn't hold. Can have multiple reasons why this doesn't hold. It may be that you have a multimodal observation. You say, either I measured the landmark is 1 meter away or it's 20 meters away. I simply don't know exactly. Maybe because it's due to the data association ambiguity. You simply do not know which feature is it that I actually observed here. Or you already committed on a wrong data association. Say, hey, this is this feature, although it's a completely different feature. So you will get so-called outlier observation, which is far away from what the real observation would be. And as you will see in some small examples, having these outliers in your optimization problem is something which hurts dramatically, which actually can screw up your solution. So already a few outliers can lead to an environment model which is completely unusable for doing any navigation task. So where the geometry of what you computed doesn't fit to the real world geometry anymore. And one of the questions is actually how to handle that. So as we said, what we are doing here, we are minimizing the sum of the squared errors terms. And as we have seen so far, this is the same or strongly related, depending on how you formulate that, to a maximum likelihood estimation in the Gaussian case. So if you take into account your prior and all the things correctly, what you're doing, you're estimating the mode of the high-dimensional Gaussian distribution about the poses of the robot and the landmarks. So you're finding the mode of a Gaussian. The problem is if you have outliers, so let's say I measure always, let's say, the distance to the wall. This is kind of now 1 meter, 1 meter 10, 99 centimeters, 1 meter, 1 meter. Now I have an outlier 100 meters. That's actually something which screws up my solution dramatically. And I get a completely wrong estimate on what the environment looks like. And the other thing is that we are completely restricted to Gaussians. Even if I say maybe 1 meter, maybe 100 meters, because there are two walls. Because let's say I'm standing at a corner, so either my laser beam hits one of those walls over there, or it goes out through the glass pane to the next building. So I'm either measuring here 2 meters or measuring 200 meters. It would be nice if I could say to the system, it's either 1 meter or 2 meter or 200 meters. I simply don't know. Take into account a distribution which is not a Gaussian with a single mode, but why not taking into account a multimodal distribution? So if we would have the possibility to integrate a multimodal distribution here, that would actually be nice, beneficiary. And what I want to talk about here today is ways for, ways for doing that, for being able to integrate first multimodal distributions, and second, having the ability to deal with outliers. So given that a certain number of constraints are outliers, how can we actually fix this problem? So why is this a relevant problem or something which actually occurs in real situations? The first thing is places may look identical, although they are not identical. If we're here in this lecture room and we're in the next lecture room next door, they look very, very similar. It may be very hard for a robot to distinguish that we are here, whatever, in room 18 and not in room 16. So the robot may generate a constraint which says, I'm here in room 16, although we're in room 18. Or it says, I'm either in 16 or 18, I simply don't know. It's one of those two rooms. Other things is if you have structures in the environment and there's a lot of clutter in the scene, and the clutter, even if it has a repetitive pattern, may lead to a multimodal belief about what the relative transformation between two poses. Let's say, or you walk along whatever a corridor with very little feature, very few features. You only have, let's say, some pillars which are standing around, but the pillars show a repetitive pattern. And you don't know exactly where you are, so you get a multimodal belief where you can be. The other thing is GPS can even be problematic if you have the so-called GPS multipass problems. You have reflections of the GPS signal based on large buildings. So you may get beliefs, or you may get outlier measurements, and the question is how can we actually take that into account? It's not always easy to get this information out of your GPS because typically it runs a Kalman filter internally, or most of the GPS devices do that, so they get a Gaussian belief is screwed up. But if you get the the raw measurements, you may be able to do better by allowing for multimodal distributions in here. So there's one small example. So there's a small robot which moved through the 3D world, and this is what is similar to this repetitive structure that I was talking before. If you move through a corridor, the robot can be actually sit here, or here, or here, and its local perception will actually match quite well. So you may get one of those multimodal beliefs where you say, I mean, the mode is roughly where the mean of that Gaussian would be if I would approximate this function by a Gaussian, but maybe I'm ending up here in another mode, and that may be suboptimal. So having the ability to take into account multimodal beliefs is actually helpful. There's another real-world example. So this is the Intel Research Lab dataset that you have also experienced. And if you look to those poses over here and the poses down here, how those individual structures match, if you just apply, let's say, scan alignment, you may say, this may match. So maybe someone has opened the door which was closed before, or here is a door now closed which was open. All the other scans map actually quite well. The same holds here. So even as a humanism, you say, okay, there is definitely a misalignment between the scans, so they don't fit perfectly, but that's something which actually can result from small changes in the environment, a person walking by, maybe closing or opening a door, that you simply don't get the perfect alignment all the time. And this can lead to a wrong constraint. I say, hey, what I see here looks exactly what I see there, so I create a constraint here in this case between those nodes. So here 2 constraints are generated, although they kind of are swapped. And this will kind of distort the whole map. So this is how it looks like. So this is, all constraints are correct except this single red one over here. So this is a single constraint. You can already see that you don't have a straight wall over here anymore. So it's kind of bended a little bit like this. Due to this single constraint, which obviously has a really, really large error. So the least square error minimization at the error is a squared error term, tries actually to minimize that. If we add, whatever, 1, 2, 3, 4, 5, I think there were 10 constraints, 10 wrong constraints. The map actually gets so distorted that it's unusable for navigation, at least down here. Here you still may be able to navigate with an autonomous system. But if you have 100 constraints, you end up in situations like this. And so the original number of constraints, I don't know how large it was, but I think it's around 3,000. Something like this along those lines. So the number of constraints that the system generates is around 3,000. If you put already 10 wrong ones in there, it's quite likely to screw up. And with 100, which is still a very small number compared to 3,000, or just a small fraction, you will actually end up in dramatic mapping errors, so that the system is unusable. So having good data associations is really important. So already screwing up a small number of places is something which can hurt your optimization if you don't take that into account. And what I would like to talk about here today is how can we take this information actually into account. So how can we deal with the problem that we have places which look identical, we have cluttered scenes, we may have GPS multipass problems, so the signal gets reflected, for example, at tall buildings, and in this case screwed up the measurement. How can we incorporate that into the graph-based SLAM approach? The problem that we actually have is if we look to our to an individual constraint. So the likelihood of an observation given the current configuration of the nodes was a Gaussian distribution. So that's what we had before. If we now say, okay, we would like to have simply a sum of Gaussians in order to have a multimodal constraint. So some of those constraints are multimodal. We simply have a sum of Gaussians. Right? That's the first attempt to solve this problem. This would be our probability distribution. What is the problem with this probability distribution? So I say, okay, some of my constraints are these multimodal constraints. I will simply go ahead and implement that. What's the problem that you're going to experience? If you make this assumption, so we know how to solve that, right? This is what you know how to solve that. That's what we did so far. Let's say I want to go from here to here. What's the problem that shows up if you want to do that, if you do it exactly that way? You start coding your stuff. At some point, you say, something doesn't work here. What is that? No, it's not. No, it's not. That's not about the dependency.
Sum is always problematic for probabilities.
You're on the right track. So the thing is, we have a weighting term down here, so we make sure that it sums up to 1. So we assume we have normalized this. Well, the sum is a pretty good starting point for when searching for problems. In this case, what's the problem with this sum? So we don't have a single constraint, we have a number of constraints, right? 100,000 millions of constraints. How do we combine those constraints? If we minimize the squared error, what are we actually doing? If you're minimizing the squared error, we are minimizing this expression over here. And this is the log likelihood of this expression. What's the log likelihood of this expression? The log will sit here in front. We can't move it inside. So if we have this number of constraints, this is a product of Gaussian distributions. If we compute the log likelihood, this turns into a sum of the exponents. Therefore, we have these sum of the squared error terms. We simply can't do that down here. You still have the log over the sum over the x of the individual terms. So if we go to the negative log likelihood, we're going to optimize. We have this term here, minus a constant. And here, we can't go further than that. That's a problem. That's where it fails. Do you see what is the dirtiest way for you to fix this? Let's say you started implementing that. Your implementation is done. You here said, oh, damn, I can't do that. What would be the ugliest trick that you can do in order to make that work?
Moving the logarithm inwards?
Even worse.
Making log and excluding?
Sorry, making the?
Deleting log and x.
No, that's not what you're going to do. I mean, the sum is kind of the bad thing. What can I do with the sum instead of the sum? Can I get rid of the sum in some nice way? Sorry? Oh, the integral, if I go from sum to the integral, it actually makes our life typically worse. So that's not what's going to fly. You have a sum of Gaussians, so it's a weighted sum of Gaussians, what you have in here. You want to get rid of that sum. How could you do that? Okay, simply say, okay, I have that sum of Gaussians. I simply ignore all of them except the most prominent one.
Take the maximum?
Exactly. We replace the sum by a maximum operation. We just take the one which currently seems to be the best one. We may flip that during our optimization. So the error term may commit to a different mode in every step of the operation of the optimization. But the key trick is to simply say, I just say where I am right now. The approximation error is actually kind of small if the Gaussians are quite separated from each other, if the modes are quite far away from each other. We say I'm either measure 2 meters or 200 meters. So either the 2 meters are currently the dominant one, or the 200 meters are the dominant one. If one mode would be 2 meters and the other one 2 meter 5, then this may not be a good approximation. But what we're going to do is we say, okay, just select the kth mode, which is currently the best one. So it's a maximization operation. Again, so if the means of these Gaussians are far apart from each other, the approximation error isn't that big. If they are near each other, disaster. Or disaster, but may have big errors. And then because the nice thing is if you move the max operation in here, if you're maximizing a function or you're maximizing a log of that function, it's equivalent. So we can move the log in there and then have our problem solved. That's kind of a nice thing. So if you compare that, so let's say we have two possibilities here which may look like this. If we go for the max mixture, so taking exactly this expression over here, this would be our distribution. So it's always the max of these two functions. Therefore, you have kind of this not so smooth position over here. If you compare that to the sum of Gaussian, it looks like this. So the approximation error that we do is, in reality, we have this situation, but we approximate it by this situation. If we're anyway just looking for the mode, maybe the approximation error is not too big. I mean, here, the two Gaussians are actually kind of close to each other. If they are further apart, this value actually goes down nearly to 0, and this value again nearly to 0. So the approximation error isn't that huge, actually. And so this is the idea of this max mixture approach, to actually change the optimization from a sum of Gaussians to a max of Gaussians. So since we don't have the sum anymore, we only have the max in here. And so then the log, if you go for the log term, I can move the log inside. So you vanish here and just have this constant factor, which I had before as well. Or negative log, if I'm minimizing negative log likelihood, this is exactly my expression. So I stick with exactly the same operation here. The only thing I need to do whenever I compute the error function, I need to pick the mode of the Gaussian which gives me the best performance. That's actually a really nice way to handle this problem, quite practical. Because if I need to integrate that into a current optimization system, I can actually do that very, very easily. The only thing I need to do whenever I experience one of those multimodal constraints, I don't compute the error, I have to compute the error for every mode and simply select the one which has the best performance. So it's just kind of a sum over the individual modes of that Gaussian distributions. And then I perform the optimization as I was doing that before. So the rest stays exactly the same in my code. The nice thing is that actually between iterations, the system can swap between different modes. And therefore, although the optimization in one iteration takes into account only one mode of the Gaussian, as you can switch the modes, you still have the ability to deal with multimodal constraints. If I do that, that's what the result looks like. So this was the original stuff you've seen before, one wrong constraint, 10 and 100. If I go for max mixtures, and I say either it's a perfect fit or it's a very, very, very flat Gaussian. This can be inlier or outlier. So you have a Gaussian distribution around the kind of, if the constraint is somewhat in line with what you expect, or somewhat in line with the current configuration of the graph. But if it's far away, it's a very, very, very flat Gaussian, so it doesn't really hurt a lot. If you do that, so all these constraints are bimodal constraints. One is the original constraint that you measured, and the other one is a flat Gaussian with a large uncertainty, which is kind of in the system swaps to this other one if it is an outlier. Well, there's a very high likelihood it will swap to that, unless it's an outlier, which you have a bad initial guess, and the bad initial guess is in line with the outlier, then you may run into problems. But if you do this, you can actually add 1, 10, 100 constraints, and those are constraints which simply swap to the other mode and don't harm the optimization much. The solution may be still a little bit different than the one which is done completely without constraints, because you still have this very, very tiny error, but it's actually kind of within the noise that you typically have in real-world data sets. So it's actually kind of a nice, interesting way to use this to deal with multimodal constraints. And even if you look to the runtime error, if you do the red one are the multimodal ones, and the other one is a regular solution here with Cholesky decomposition, you actually have a very similar performance in runtime. So you don't increase the runtime a lot by just checking for those individual constraints. So when you evaluate the error, the evaluation of the error is somewhat more expensive because every constraint can be multimodal or bimodal in this case, but there's no big difference in the operation of those systems when you if you use the red or the blue plot. This is exactly the trick that is used. So if you just want to deal with outliers, so the red one is kind of the inlier, and the blue function is the one which is the outlier. So this is a bimodal distribution it's a bimodal distribution, one for the inlier and the other one for the outlier. So red is inlier, blue is outlier. You can also handle those cases where you say, I'm either there or somewhere else. So you have a bimodal distribution, mode 1, mode 2, or I have my blue curve, which is again the outlier. So I still can handle these multimodalities and be able to deal with outliers. Or we can even do things for odometry. If you say, especially if you start up a robot and the ground is muddy, the wheels may slip before you get grip and the robot starts driving. If this is the case, although you execute in command, you're standing and then you start moving. So you may get this kind of distribution. So in most cases, actually the vehicle executes what you tell the vehicle to do, but in some cases it simply doesn't move. And you can even handle this in odometry constraints with these multimodal constraints. So this max mixture idea is actually a pretty easy idea, pretty simple idea. Just funny, no one has done that in robotics until recently, a few years ago. The first one was actually Edwin Olsen and Pratik, who came up with that, Pratik Agarwal, with this idea of using max mixtures, because it's a very simple trick. It's perfectly integrated into an existing system. It has quite some nice properties, and it's actually a smart idea. So when reading this paper, you say, why was I not the person who had that idea? But because it's actually really easy to do, and this actually supports these optimization systems quite a lot. So it's actually a nice thing. So the nice thing is it can handle both things at the same time, data association errors as well as multimodal constraints. You can argue that multimodal constraints in practice do not happen that often, that really your measurement is really multimodal. You'll have to look for cases where your sensor property or the sensor reveals these properties. But there are some situations where there's a case and you can actually do that flexibly in your system. So the combination of outlier rejection and dealing with wrong data associations is actually kind of nice. You also can do this obviously in 3D. So this is again this data set with the sphere that we have seen before, a robot moving in a virtual sphere with constraints. So this is Gauss-Newton, and this is the max mixture Gauss-Newton. And so you can see here there's a non-perfect alignment in here because you don't see the regular structure. This results from a single outlier constraint, which I think connecting those nodes over here. Here you don't see that at all. And as you increase the number of outliers to 10, it's hard to identify the sphere here. And if you increase this to 100 outliers, this is just whatever, a big mess, whereas this one still is able to solve those things quite nicely. So there's one way for dealing with these outliers. There have been other techniques which have been proposed in order to deal with those outliers. And the second technique is dynamic covariance scaling, which you can actually do. So this was this is the equation, the minimization that we do in the standard squared error minimization, as well as sum of squared errors. And the key trick of dynamic covariance scaling is just replace this information matrix here with a variant which has a scaling factor. So a constraint-dependent scaling factor added to that. And the key idea, the intuition behind that is, if I have a constraint which has a large error, so where the current configuration is far away from what the constraint tells me, just reduce or increase the uncertainty that is associated to that. So decrease the information matrix. So scale down the information matrix. So again, just a small change by saying, the question is still, how do we actually compute these? So the main change is we go to this formulation, we have the scaling factor over here, and you need a good way to compute this scaling factor. So how can we actually do that? And there's actually a closed form. You can derive that under certain properties where you end up with this operation here. So this is just a free parameter that's here, and this is kind of the original error, the chi-square error. So this was this term over here. So what you do is you compute the original error, then you compute this Sij and just multiply your information matrix with this. This leads to the case that constraints which are far away from what we expect have a smaller influence on the optimization. So we can actually visualize this. So what you see over here is, so this is the black curve is the parabola which results from the squared error. This is the value of this scaling function s. And the red curve is kind of the scaled error. So taking the black curve multiplied with the corresponding blue value over here. So in this area, kind of the core center of attraction, both perform equally well because there's no scaling involved. But the further you move out, the more the red curve gets scaled, so it gets kind of fatter and fatter and fatter. So, and if you evaluate for one point, let's say for this point over here, that would be the original error term, and this is the scaled error term, which sits somewhere here. So the error is weighted down the further I'm away. However, we still have a linearization point. So if I compute the Jacobian over here, I still have a Jacobian which drags the system into the right direction. So even if I initialize that quite far away, I still get kind of pushed into the right direction. We have a small video where we see how that works exactly. So if the error increases, if you're further away from the mode, this is what your error function looks like. So the further you're away, the more you downweight the influence of this constraint, because you increase the uncertainty of this constraint. So if you consider the Gaussian distribution, you can generate a flatter and flatter and flatter Gaussian distribution the further the point is actually away. There's also one technique which you can find, which is also quite easy to implement because you just need to compute the scaling factor and multiply that with your information matrix for every constraint. Also something you can do quite efficiently. Okay, if we look a little bit more into kind of is there an overall framework which brings this together, the standard optimization, and what I've shown you here is that the problem that we have in this Gaussian distribution, and this holds for the max mixture as well as for DCS, is that kind of the tails of this Gaussian distributions contain too few probability mass. They're too close to zero that it's very unlikely that you are really far away from the mode. And therefore, if you have one outlier which is really far away from the current estimate, the whole mode is dragged in this direction. That's kind of the problem that we have with this Gaussian distribution. And therefore, especially terms with large errors, so if you have constraints which introduce large errors, these are these outliers, this can actually screw up the optimization when computing the minimal error configuration. So one way you can do is, or it fits into the framework of so-called robust M estimators, which intuitively say, okay, we don't assume a Gaussian distribution, we assume non-Gaussian noise, and especially we have bigger tails of this distribution. And typically one uses the formulation that the likelihood is, again, an exponential function minus, and then we have this term rho of the error value over here. And that what I'm going to minimize is actually this expression over here. So I have this function rho, and I can encode whatever kind of noise model I want in there. It still depends on the error term, and it's still an arc-min operation over the sum of those terms, so the log likelihood. So this is something which is a little bit problematic for, or the max mixture framework doesn't perfectly fit in there because we replace this with this. We have still this max or min operation in there. But you can actually show that DCS is a variant of that. And depending how you select your function rho now, you get different properties in the optimization. So if we use, if rho is just the quadratic function, then we actually have the original problem. That's what we minimized, x of minus squared error. So if we have this one, we are exactly in the Gaussian world. And now there are different techniques how we can actually address that. One thing is we could take simply the absolute value, so we don't square it. Just take the absolute value of the error. It's not the parabola that we have, but the absolute function, the absolute value of that function. You could also use a so-called Huber M estimator. Then the function is a parabola if the error is small. So if the error is around the minimum error configuration, it's a parabola, but outside it's just a linear function. So you have the parabola in the middle and then a linear function outside that. You can also say then at least if you have an outlier which is further away, the error doesn't grow quadratically, it just grows linearly. So it's a very popular function. There are several other ways. If you look to the literature, there are a large number of those so-called kernels which are introduced in this system in order to get a better behavior or meet certain error characteristics that your system actually reveals. So this is an example for the Huber cost function. I said we have this parabola close to the, so in the, around the zero error configuration. So if the current configuration is close to 0, I have the parabola, and here it goes into some straight lines. And this is just an example of different ones. So this was the L1 norm we said before. Quadratic is just the quadratic function was the original that we have. This is a Huber cost function. You have other cost functions which are again a kind of parabola here and then are flat over here, or which approach a flat line like the Blake-Scissorman kernel, Cauchy, corrupted Gaussians. So there are different ways of kind of row functions that we can actually plug in there and that we're then trying to minimize. And so if you look to the max mixture approach, it's actually kind of similar to this corrupted Gaussian. So if you plot both of them together, so this is the corrupted Gaussian, the blue one over here, and the red one over here is the max mixture. I still have this max operation when I switch, so it's kind of the max mixture for a bimodal distribution for dealing with outliers. You still have this jump over here if you jump from one mode to the other, which is here kind of non-smooth. But in all other areas, those two functions actually, at least if you compare how the kernel looks like, this is actually pretty similar, or the function that I'm going to optimize in the end. They are actually both pretty similar. And the same actually also holds for the dynamic covariance scaling. We can actually show that dynamic covariance scaling is a special of these robust M estimators. So, and in this robust estimation, the choice of this function rho kind of encodes the noise properties that you expect. If you take a quadratic function, you live in the Gaussian world, and depending on what your noise properties, do I have outliers? And how many outliers do I have? Or what certain patterns do I need to respect when I do my optimization? You can change your rho function. That means you're leaving the Gaussian world. And so the system optimizes according to a different cost function. But this allows you to take into account, for example, these heavier tails, so that outliers still are not weighted that dramatically and impact your solution so much because they completely disagree with the solution that you actually have before. So the Huber cost function is, some cost functions is often used. This is the parabola close to the mean and the linear function outside. And then there's max mixture, which is quite similar to a corrupted Gaussian. It still has the advantage that it can handle multimodal distribution, which is kind of a very nice property, a property that I like. And for dynamic covariance scaling, just as a note, this is similar to a robust M estimator of these families that we have seen. It's actually an equivalent that you can show. So actually, to sum up, we don't have to do a lot of really, really bad things in order to deal with outliers. Of course, we are leaving the Gaussian world if we do that, but this simply means we have a different assumption about the noise that we're going to experience. But I can quite nicely integrate that here, or a lot of those kernels can be quite nicely integrated into this least squares framework, where you just change your error function in a certain way. So you still have your exponential function, but you only change this rho function in the exponent to still be able to optimize the log likelihood. So this rho function goes into the log likelihood, but you still can compute the logarithm, which is something you need to do in order to come up with an effective minimization procedure. I just picked out two examples here. One was max mixture and this dynamic covariance scaling, which have been proposed in robotics, but this robust M estimation is something which was not invented in robotics, which comes from different fields, or from numerical optimization, or some from computer vision, like the Blake-Scissorman kernel was one of the kernels which came from computer vision. And they are a quite attractive framework to deal with outliers, and in most realistic data sets and situations when you deal with robotics, there's a non-zero probability that there will be data association error in there. And the more likely this data association error, the the worse it gets if you optimize without taking these outliers into account. And that's actually an easy way to integrate that, and often actually requires not that many code changes, so you can actually adapt a current system which cannot deal with outliers to systems that deal with outliers. Just picked out 2 examples here in terms of literature. This is the max mixture approach by Edwin Olsen and Pratik Agarwal for this robust max mixture, as well as the dynamic covariance scaling, which is another alternative on how to weigh down the errors if you're far away from the current estimate. And this is actually equivalent to performing a robust M estimation with a specific rho function in there. So that's kind of, I know this was short. On the other hand, it wasn't too, the idea should be clear to everyone what happens here, that by changing this function, you get much better behaviors. Kind of deciding which function to use for the underlying optimization problem is not always an easy choice. So this requires some expert knowledge, some good intuition on coming up with one of those functions. But max mixture works kind of nice. This dynamic covariance scaling has also been proven to work quite well. And but also the Huber kernel is some standard choice that you can select if you do this error minimization. Okay, so that's it from my side for today. With this lecture, we actually finalize the kind of back-end, looking into back-ends for SLAM systems. And next week, which is the last week of the term, I will briefly talk about front-ends and give kind of a short summary on what typical front-ends exist. Obviously, with not going to all the details as we did that here for the back-end. This is also one of the reasons is the front-end strongly depends on the sensors and the assumptions you do in there. So generalization from one sensor setup to another sensor setup can be quite tricky, but the back-end itself, which sits here, doesn't really change that much. Therefore, the focus in this course was much more on the back-end, but at least I would tell you a little bit about what typical front-ends exist and how you could realize a front-end if you want to build a SLAM system, but that's something we are going to do next week. That's it from my side. Thank you very much, and hope to see all of you next week. Thanks.